Let's talk a tale of two histograms, the best of response times, the worst of response times. It's a Charles Dickens' Tale of Two Cities reference. Don't have to get that, but it just sounded like a cool title. I'm going to start with an apology because this is a very geeky, I submitted something that I thought something just really geeky talk proposal, some obscure statistical methods, and then Jason decided to inflict it on you on Monday morning. So if you haven't had enough coffee, I'm sorry, right? So we're getting into some odd things here. And then just briefly, you can find me on Mastodon or on the Slack channel. I'll be around till Wednesday afternoon. So I want to sort of follow up. This is a sort of launching some ideas here. And then just the other thing is, I used to work for all these companies. About a year ago, just before the last Monitorama, I quit my corporate day job working for Amazon and now sort of independent, sort of retired consultant, whatever. So you see Orion X on my .NET. That's basically a sort of a consulting advisory analyst sort of group of a handful of people that gives me a sort of a vehicle for doing things, but that's basically it. And mostly I'm doing conference-driven development. So I get really busy because I put in a proposal and I checked in some code into GitHub this morning, so there you go. Back at the end of January, I had to do enough work that I thought I could actually turn it into this talk. So I blogged it and I put it out there, and that was my sort of down payment on this event. So there's a blog post, basically percentiles don't work. And I'm talking about the analysis of response time distributions. And I've interposed this where there are pictures of sunsets, so you've got some eye candy, some things to look at. So what is wrong with response times? And it's really, these are the two histograms. That most people think response times look something like this. You've got, sometimes it's fast and then there's this long tail of it getting slower and slower. But what it actually looks like is more like this. And I constructed these to have the same sort of mean and maximum. But what you find is actually they tend to be spikier and have multiple spikes and then have a longer, flatter tail. Right? That's kind of the way it looks. But this is kind of hard. It's hard to see what's going on there. In fact, even the resolution on this monitor, on the display, it's not showing it very well. So the problem is that you get a small change in load leads to a large change in response time. And if you've got like an SLA that says we will respond 95% of the time within 2 seconds or one of those SLAs, you say, well, how much more load can we take before we break our SLA? And it's very hard to model that. An average response time isn't useful. So people use percentiles. But then percentiles actually don't work that well either because small changes in load move your percentiles around a lot. And then the other thing you get is like a 95th percentile calculated every minute, but you're summarizing by the hour and you average them together, and it really isn't a percentile anymore. It's like an average of what used to be a percentile, but statistically it's actually a meaningless number. It might be useful, but it's not a percentile, so you have to watch out for that. But the thing is, there's a lot of interesting structure in response time distribution. This has been bugging me for a very long time. So if you remember your high school stats, right, there's mean, median, and mode, right? So median is the 50th percentile. So if we're doing percentiles, we're kind of doing median-like stuff. Mean's the average. So you can see the mean is, on this one, is a bit over a second. The 90th percentile is, whatever that is, like 3 or 4 seconds. But the modes are the interest. There's 3 modes here, right? There is the spike, a short spike, another spike, and another spike. So what I care about is, those are the most common, that's the most likely thing to happen, is something that's going to be on that spike. That's the most probable thing, right? So, but we don't generally use modes when we're talking about response time. So what I've developed here is a way to try to figure out how to manipulate and figure out the modes and manipulate them. And that's what this talks about. So then, why is there structure in response times? And it's basically because requests that come into a system take different paths through the system, right? If you've got microservices, they're going through different services. You've got some queries are heavy load, some are light load. You look at an API front end, it's got this big mixture of things hitting it, and they all respond differently, and you combine all those together, and so you wouldn't expect to get a single smooth response time distribution. And the key point here is the word mixture. It's a mixture of underlying distributions. So back in 2016, I gave a talk where I simulated response times to show this. This was at the Micro Exchange event, which is in Berlin. And it's actually in some slides. I rolled it up into my microservices tutorial slides I did at the end of 2016. So you can find most of my slides are on GitHub nowadays. I'm still waiting for GitHub to support PowerPoint as a file type, but maybe they'll get there eventually. This little diagram below is from this deck, but think of a load generator that hits a web service, and it's got a memcached, a MySQL, and a disk volume, right? And depending on what request you send it, you might find the data in the cache. You might be able to satisfy the data directly from MySQL's cache, or you might have to go to disk, right? And then those three things take different lengths of time. And there's this spreadsheet-based thing. You can just go to this URL and play with it. It's a Monte Carlo simulator, and Monte Carlo, if you want to combine together response times, the technique you use is called Monte Carlo simulation. You have a bunch of different distributions. You can sort of combine them together into a final one, and that's what this is doing. So on the left, you have the overall response time, and I'm sort of modifying, so combining together the distributions of the different things. And it's a bit clunky, but it's interesting. So if you look here, underneath all of this stuff, you can kind of see this fairly blocky distribution. So if you hit the memcached, you get a nice fast response. And then a bit later, you see there's the MySQL cache hit, and then there's this much slower, I had to go talk to the disk, right? So there's 3 spikes in this response time, and then there's this weird gibberish thing you had to put in to make it do that. So anyway. But if you change the response time, so one of the things I can do in this is you can tweak it. So if you look at the sort of shape there, this is 580 whatevers, and then if I increase the memcached hit rate, it's 480, right? And if I decrease it, it goes to 740. So it's basically simulating the overall average response time, and it's playing around with the distributions. So I can take individual responses and combine them together to show that I get these sort of multimodal peaks. But what I really want to do is start with a histogram and do the reverse direction, and that's the thing I couldn't figure out how to do. And actually, I was at last year, I was talking to people here at Monitorama saying, how does this work? I mean, this must be a statistical technique here, and it probably has a name. I couldn't figure out what the name of the technique was, and I was talking to statisticians, and my dad is a retired statistics professor. I tried explaining it to him, and he went, yeah, I retired 30 years ago, I've forgotten all that stuff. So that didn't work. But so then earlier this year, like in January or something, I was just, Danny Burkholz was on Mastodon, and we were just chatting, and he knows R, and he knows statistics, and I was asking him, I was trying to explain to him what I was trying to do, and then Ed Baraski, who I'd never heard of before, just pipes up and said, oh, that's called mixed methods. Okay, and they sent me an R routine, and now I have all the stats. Yeah, great, now I know what I'm trying to do, so which is a bit weird. All right, so this is what we're trying to do. Yeah, it's a maximum likelihood method, expectation maximization of finite mixed methods, and you don't need to know any of that, it's fine. So, all right, so hopefully everyone's either sort of got deer in the headlights look here, or was going, of course, that's the way you do it. So then the question is, you're mixing these distributions. What is mathematically, what are these distributions? Because that matters, and how do you put this together? So there was a really nice blog post from like 2017 or so by Bill Kaiser of New Relic. I think he's now retired out of New Relic, or he's not there anymore, but he was, I forget, CTO or something at New Relic at the time, or a distinguished engineer or something. And he was saying, well, what shape is this? Is it log, he's got a distribution, is it log normal, or is it gamma, or whatever? And he was saying that it's really, but anyway. And then he had this multimodal distribution. He says, okay, you've got 2 modes here, and but he didn't really show how to analyze it. So, more coffee time. What would you expect? Like you have to kind of go, well, the distribution is because of something underneath is happening, right? If you have random arrivals, you're a telephone network, you have gamma distributions, and this is sort of queuing theory leads rise to this type of distribution. If you have a normal distribution, the sort of symmetric thing that you see in sort of statistics textbooks, it's easy to work with, that assumes you've got random adding and subtracting going on, right? And it goes to minus, negative, and minus infinity and plus infinity, but response times obviously don't do that. You can't have negative response times. So actually response times are always a one-sided distribution. And if you take the log of a normal, it's called a log normal, and effectively what you're saying is that the errors are adding or dividing. So it means that you're getting proportionately slower or proportionately faster on your response time. So this is kind of why it makes sense to me. So let's say you've got a system and its CPU slows down for a bit. All the requests that come through it will be 20% slower for a while. Or they'll be, 10% faster or something like that. So it's like you're turning the speed knob up and down as the requests come through, and that's what's causing the distribution. So what I'm basically saying is that if you get a mixture of log normal distributions. All right, so this is there are no new ideas, just ideas that you have. Somebody's probably already done this, I just haven't found them yet, right? But this is what I think I'm trying to do that's vaguely new here. If you take response times and you take the logarithm of them, then you're turning everything from a log normal to a normal, right? And it's a nice symmetric thing. And then I can mix together a bunch of them, and this is nice and mathematically tractable. It's easier to do. All right, so what does that look like? So that's that spiky thing that I showed you at the beginning. The actual data was collected for this particular system, was connected using a high dynamic range histogram, which HDR histograms are really, really nice package that will collect histograms for you. The bins in the histogram double as they go up, right? So it's a logarithmic histogram, right? The really fast bits are down sub-microsecond or millisecond, but the bins out here are like tens of milliseconds or seconds apart. And when you do that, you're effectively, when you just plot it as bins, you end up with effectively, you've got a log normal distribution. So when you just plot the histogram, you get this nice shape here. And I was staring at that saying, those look really symmetric and that looks like a normal to me. So I actually hand-fitted a bunch of normal distributions to it, which is the plot on the right. And that sort of was my sort of starting point for this, was saying it looks like if you fit multiple distributions to it, it works. All right. So the statistical tools for doing this expect you to have the underlying data and to run it through that Greek algorithm thing that I showed you. But quite often you've got millions of data points happening. If you've got a really high throughput website, you've got millions of requests coming in and you've just got the histogram. The underlying data is too much. All right. And even if you do have the underlying data, it turns out that the tools want to have a first guess at the peaks anyway for the algorithms to work. And I really only want a rough guess of the peaks. So in the end, I'm just ignoring all that Greek methodology and brute forcing the thing. So this is, I was trying to find the real algorithm that would really do this for real, and in the end, I just brute forced it. Anyway, so I'm going to start with either a histogram with exponentially increasing bucket size, which is kind of what you'd find from HDR histogram, or a log file that's got timestamp, latency, and then hopefully a tag for what kind of query was going through it at that point, right? Just those three figures, and you just got a whole bunch of those. And then I can just make a histogram out of that. So I got some code, I wrote it in R, it's called aspeak, so it takes this log of data, and log of latency, and it finds the peaks for it. There's a whole bunch of stuff here, but basically you see it's a function, you give it the histogram, you give it a timestamp, and then there's a bunch of other options. And I won't show you the code, it's about 100 and something lines of code, it's on GitHub. And this is what it produces. So I gave it the thing, and basically it says the peak latency on the right is the latency of each of the spikes in this thing. So there's something at 2 milliseconds, something at 3, there's something at 477 at the bottom, and it's basically looking through the buckets and finding them. And what that looks like if you've got a calling pattern. So the thing about this is that what it does is it keeps subtracting out. It finds the top peak, it's subtracted out, then it looks for the next one, subtracts it out. So it works when there's overlapping peaks. It's obviously clearly easy when you've got peaks that are nicely separated. You can just analyze them separately. But when they're all mashed together, you end up with a very wide peak. And so this is kind of what's happening here. So this comes from a system where there's lots and lots of calls going on that are roughly the same latency, so they're all combined together. So you've got a little bit of very quick stuff, a little gap, and this is rounded off to a millisecond, so there's a bunch of gaps in the distribution on the left. But if you look on the right, you can see a bunch of different colors. Each of those are the separate distributions I'm adding together. All right, so then the other thing is, okay, I can just do it for one system, but what I really want to do is look at how the peaks change over time. So I want to take chunks, say I've got a log file or I've got a series of histograms, I've got one every minute. How do I identify that this peak is the same as this peak is the same as this peak as I go across? So I've got some work to work on that. So I've got, as peaks will give me the individual processing, but I need to do some clustering. So I'm going to now look at, this is another system, this is a GraphQL front end. Right? So you've got lots of different request types coming into this, and it's got 3 different clumps of data, of peaks you can see, and then there's this huge spike at the beginning because there's some kind of configuration thing, which is a super quick response. And I figured I just filtered that out. So if we just forget about the sort of super quick thing, this is probably more of the real GraphQL stuff that's going on. So I've got a bunch of distributions here. So that's the response time on the left. In the middle, you can see the histogram. And on the right, you can see it fits really nicely, the 3 spikes in different colors and then some other residual bits and pieces. And then that's for all of the traffic coming through all the GraphQL traffic. But basically, I picked what's the most common actual business request. Not configuration data, but something that actually does work for the business. So this is like the most common important business thing this does, and it turns out that that data has 2 spikes. Right, that's the distribution. There's a spike on the left and another spike. If you do it on the histogram, you can see there's 2 spikes and it fits. And if you analyze this the normal way, you'd say, well, the minimum is 8, median's 40, the mean's 240, and I've got my percentiles, and I can analyze it like that. And nowhere in that data does it tell me I have 2 spikes and what the characteristic of those spikes are. All right, so I'm a bit theming here off of Tale of Two Cities and the French Revolution, which is where it's set. So I have a guillotine algorithm, which is going to chop off the head of the log file in chunks. You give it a log file, and it chops it up into 1-minute chunks, processes each chunk separately, and then tries to flow that across. So the 2 peaks that I actually have, once they're processed. So one of them, minute by minute, this is just the first 5 minutes of a 15-minute thing, it's about 18 milliseconds, that peak on the left. And the peak on the right is about 430 milliseconds. Right? Just for the same business request is hitting the system. Sometimes you get an 18 millisecond response, sometimes you get 430. I actually have no idea why. Maybe it's caching the results, and some of the times you get the fast response, or I don't know. But it's very distinctively 2 different response times. And the thing is that what's actually going to happen over time is that the ratio of those 2 are going to move about. But when the system feels slow, it's not usually that the 18 milliseconds has suddenly become 25 milliseconds. What's actually happened is the proportion of the 2's changed. Right? So what you're seeing over time is the height of those 2 spikes is changing. The position of them isn't changing. So if the position moves, it's probably because you did a code release and you changed the code path, right? But a lot of the time it slows down because the ratios change. So here's sort of the same thing coming out of these chunks. There are 15 little plots like this, and then I find the spikes, and you can see, there we are, right? So the leftmost spike is that position, that one on the left, and then the big spike's the one over there, and the bit that's hanging off around a bit slower is down there. So this is a clustering algorithm. It basically, it looks at all of the peaks and it says this is near enough to this must be the same one, because the numbers aren't exactly the same. And you can see that the height of the data is moving up and down. The height of the peaks is moving up and down, but they're not moving side to side very much, right? Over at least this fifth. The system I took this off was actually struggling a bit at the time. There were some issues going on, and there was some variation happening. So then, and I'm still working on this, if you've actually decomposed this, you can actually reverse engineer the actual percentiles over any time frame by reconstructing the distributions. And I've been working on that code. I haven't quite finished that yet. But this is what it looks like over time. So if you look at those little dots on the left, this is the dots sort of moving around. And you can see, they're roughly the same. And then at some point towards the end, the orange cluster drops and the blue cluster goes up at the same time. They sort of diverge. So the ratio of the two moved a bit towards the end of this time. All right. So what am I trying to teach you here? First of all, that histograms or response times, I think they contain a lot of interesting structure. That you should not ever treat response times. If you're processing anything to response times, it's really good to do the logarithms of them or use a log-based histogram. It'll give you, it's a much more tractable sort of value to work with. I think the peaks are interesting, and what I've seen from a number of different systems is that the modes, latencies tend to be stable, and a lot of the variations we see in response time, our distribution, are the probability of each mode changing rather than the position of the mode. This is all on my GitHub account. So, next steps. If anyone wants to help me play with this, like I say, I'm a free agent, I do whatever I feel like nowadays. So I'm happy, or if anyone wants to implement this, most of the code I wrote here was written with ChatGPT. I just like, how do I do this in R? And it's like, gives me a page of code. And if you want it in Python or something, just give the code to ChatGPT and say, I want this in Python, and it'll probably work. It seems to, it's amazingly good at doing so. This is the free version of ChatGPT. I'm just throwing stuff into it. So that's been pretty interesting. And then I've got the final quote. I started off with the opening quote of Tale of Two Cities, and the final quote. It's a far, far better thing that I do than I've ever done. It's a far, far better REST API than I go to than I've ever known. I just had to add the letters API was anything I needed to modify in that quote. All right, so that's what I've got. We've got a few minutes left. If there's any questions or discussion, I'll be around the next few days, and I apologize for this being the first thing you had to sit through on a Monday morning. But hopefully the sunsets made it okay. Any thoughts, questions?
Got like 5 minutes or so. I think there were some questions out there. Yeah, go for it.
Did you actually find out what the spikes were from?
Did you know where the spikes were from?
In this particular case, I haven't dug into it. I mean, I've got lots of data I've collected over the years, and I just keep going through random collections of data and trying them out. Primarily, it's like I said, it's usually, if you've got two modes for the same request, it's usually a cache hit, cache miss situation, and you can reverse engineer a cache hit ratio out of that one way or another, right? And it could be, from a code point of view, it's sort of somewhere in the system, it's already got all the data. So those are the fast modes, and it usually has to go to disk or storage or something is the slow mode, and that's a very common situation. But yeah, and the thing that's encouraged me is pretty much all the data I've seen, it's really works well for fitting those normal distributions, the log normal distributions, regardless of where I've got the data from. I've tried a bunch of different systems. This data I've shown you here is from 3 or 4 completely different systems, and it seems to work reasonably well so far.
Awesome. Any other questions out there? Anything from the top? It's kind of hard to see, so just wave your hand. Oh, I see one back there. Great.
So have you applied this to like other data that's like time oriented or any other kinds of interesting data to this model that you've built here, like build times in a CI environment or other things, and seen similar patterning or anything like that?
So the question was, have you applied this to other data sets? If I summarize that right for the stream?
I haven't got data for that, but we're certainly happy to try it. Basically, anything that is modeling a response time that's going through a system that tends to speed up or slow down, right? That's the model that I'm assuming here. So yeah, a CI system should probably do something like this too, right? But the thing about, you'll see response times, yeah, normally it takes 8 milliseconds. Every now and again it takes 20 seconds. Like, what the hell's going on? What's this long distribution thing? Well, there's some weird mode out there which just suddenly got a little bit more traffic to it. So one of the things that the code doesn't, it does identify these really long tail peaks right now, but that's sort of another area of investigation to see if we can just focus on these really, the way out there. Like, why is it suddenly you get, what is going on with the extremes? Like, if you trim all the data to the 95th percentile, you're actually ignoring the 5% that's most interesting, which is like, why did this really take forever? If you know why it took forever, you can quite often figure out how to sort of dramatically improve the response time of something. Because it's the long tails that cause the timeouts that screw everything up. So that's kind of the way I think about it.
Great. Any other questions out there? All right, I don't see any. So if I'm missing you, yell at me. No? All right. How about another round of applause for Adrian?
Okay.